A very good morning to everyone. Welcome to our presentation today, which is Next-Gen PCIe Active and Passive Cable Solution for Enhanced Signal Integrity and Reach. So today we are a total of 5 presenters to this paper, and out of which 4 are here right here. So as an overview, this paper will be presented in 3 sections, starting with passive internal cable, moving on to active external cable assembly, and then active internal cable assembly. Starting with passive internal cable solution presented by myself, Ashika, Pandankeril, Shaji, and co-authored by my colleague, Calvin Feng. We both are from TE Connectivity. So internal cable solutions play a crucial role in server and storage applications in systems that utilizes OCP NICs, PCIe add-in cards, and EDSFF, etc. And as PCIe technology advanced, you can see that in Gen 6 and Gen 7, it utilizes PAM4 technology. And you also see that the Nyquist has been doubled there, making it extremely challenging. And you can also see that you also need a smaller footprint to occupy in certain applications because it's PCIe and you want to be as close to the application as possible. So you need a lower profile connector that fits in these tight environment. And looking at the Nyquist going to 32 gigahertz and having PAM4, as I said, it's going to be challenging. But the overall channel budget has not significantly improved, as you can see. If you look at it, it's just increased from 32 dB to 36 dB at Nyquist. And if that's going to affect the overall channel length, then it's going to be very crucial when it comes to a system design. And so in conclusion, you can see that internal cable solutions play a critical role in server storage applications. So you need to go to an innovative design that uses minimum space, and then that's going to be very, very important. So this slide looks at the evolution of internal cable solution and how it adapts to the needs of advancing technology. If you look at it, you can see that from one generation to another, the bandwidth has clearly doubled. You also see that sometimes the modulation scheme has also changed. Looking at Gen 4 and Gen 5, you can see that it uses an NRZ modulation, but going to Gen 6 and Gen 7, PAM4 was introduced, where the Nyquist is double and the new technology also introduces significant challenges. Looking at Gen 5 and Gen 6, even though it changed from NRZ to PAM4, the Nyquist will remain the same. And that's the reason, the same connector being used for both the generation. Now going to Gen 7, we face new challenges, right? But if you look at the previous generation, it all uses a PCB-based paddle card interface. But going to Gen 7, because of the performance requirement, there is a need to go to a different interface, more like a contact plug, so that it can meet the superior crosstalk and return loss performances. So in conclusion, the evolution of internal cable solution does not mean just to meet the increased bandwidth demand, but it also means adapting to the demands of advancing technology as well. Now let's look at some of the challenges in the existing design that would limit us from achieving the next generation performance. First and foremost, it's signal integrity. So to achieve a bit error rate of 1 to the power of -6 at a data rate of 120 gigatransfer, with PAM4 is going to be extremely challenging, right? And you can see that already the existing design must have reached its limits or boundaries, what can be achieved any further for far-end crosstalk and return loss. We also see several challenges coming from having a PCB interface because the manufacturing tolerance can lead to a trace impedance variation of about 7 to 10%, which can be huge for a Gen 7 connector. And we might have also seen the lack of control that we have on the mating zone impedance having a profound impact on return loss and roll-off frequency. We see several manufacturing and mechanical challenges as well. For example, the mating depth and mating position tolerance, contact width and space tolerance, cable terminations issues, etc. So what we need to do is we need to evaluate all of these challenges to see if the existing design can be pushed beyond its limits to see if it can be used for current generation, or if we need a whole new approach altogether. But at the end of the day, all of these challenges need to be addressed before we advance to next generation. Now let's dive into some of these challenges in detail. Firstly, the mating zone impedance. So here I'm doing a comparative study between the current generation mating interface and a probable alternative for next generation. So as you can see, the current generation uses a traditional contact structure where it uses a mating interface as a PCB. But we all know this has a well-known problem of electrical stub that comes from a mating pad stub as well as a contact tip stub. And any efforts that we take to reduce or remove these can lead to mechanical issues and failures. So how about in Gen 7, we try an alternate solution like a hermaphrodite contact structure. This uses a PCB-less interface with multiple contact points, eliminating the problem of electrical stubs from the mating pads altogether. And this kind of design also allows us to have a reduced mating contact stub. Now let's look at the data here. So the data here is not a full connector. It's where I've isolated the mating interface of both the designs so that we can see how electrical stub impacts different SI parameters. As you can clearly see in the insertion loss, the roll-off frequency has been pushed beyond 70 gigahertz, but just going to a hermaphrodite contact structure. You also see remarkable improvement in return loss of about 20 dB, and also the fraud and crosstalk resonance has been pushed beyond 70 gigahertz. So I think it's pretty evident that we need a different contact structure for Gen 7 performance. As I mentioned before, to achieve a data rate of 120 gig transfer with PAM4 would require extremely good crosstalk performance. And this is going to be challenging, especially for a connector design. Because if you look at a traditional connector, especially at the mating interface, it uses a ground signal, signal ground pattern. And also, the current design has mechanical limitations on how much more shielding and grounding can be provided at the mating interface. And this is going to be a problem, right? So how about for Gen 7, I believe it's pretty imperative that we need to have fully shielded connector with proper grounding whole throughout the connect, not from host to the mating interface. And this is going to lead to a design change in the connector interface, paving way for a new form factor to meet the next generation demands. So if you look at the comparative study here, we are evaluating the near end and the far end crosstalk. So where the comparison between the current generation connector and a fully shielded next-gen connector. Clearly, the results show that significant difference in the crosstalk performance by just going into a fully shielded and grounded connector, making it an essential for next-generation connectors. So we talked about several design considerations, and one advantage to have would be a smaller footprint that occupies less PCB space. This is going to be particularly useful for a newer chip application. So the table here shows a comparison between Gen 6 and Gen 7 footprint dimensions. As you can see, most of the single pair dimensions have been kept the same, but slight adjustments made to the ground dimensions. So one effective way to reduce the footprint would be to reduce the dimension D, which is the distance between the two rows, by 1 millimeter. So this helps us to achieve a smaller footprint, allowing us to stack more connectors next to each other. So this is like optimum usage of space, right? So one could argue, like, would this have a negative impact on near-end crosstalks? So the plot here is a comparison between a full Gen 7 connector and just the footprint-only performance. So you can see the contribution from the footprint compared to the full connector is definitely less. So kind of proving our point, this is not negatively impacting the crosstalk performance. So we discussed several signal integrity enhancements. Let's look at some of the mechanical improvements that could enhance a Gen 7 connector. Firstly, we need to make design changes to reduce the mating height of the connector. This is extremely important because this allows us to position the connector very close to the chip, mainly in applications like under a heatsink or a cold plate. So it's important that we have a low profile connector to avoid any PCB losses that can come into the whole panel budget. Additionally, it'll be good to add some contact protection features, like something that's shown on the screen, or by increasing the shielding height, because this could help us to prevent any damage that we can do to the contact during bending or any handling. All right, so we discussed several challenges and how different design consideration can overcome these. So it's pretty clear that the industry needs to adapt to a new connector interface for PCIe Gen 7. This not only improves the performance, but also ensures greater reliability for high-speed application. So this concludes my section. I'll hand it over to my colleague, Brian.
Thanks, Ashika. I'm Brian Costello from TE Connectivity. I'm going to talk about active external PCIe cables. And there's been a lot of presentations this week so far. We know AI and disaggregated architectures are driving the need to connect various boxes all together in a rack-to-rack or in a within the rack. So intra-rack cabling can support passive cables, and that's really, everyone is preferring passive. It's got a lot of benefits, and if we can use it, it's going to be used. The panel this morning talked about that as well. The active cables are needed if you're going to try to get from rack to rack as we scale out to get those distances to be able to support the speeds that we have. There's several active options that we've looked at to solve that, from redrivers to retimers to active optical linear optics as well as retimed optics. We've focused more on the linear redrivers. It has the lowest power increase over the passive cables. It's got an adequate reach, 4 to 6 meters approximately, very low latency, and the smallest increase in cost, again, relative to the passive copper. When we look at linear optics, we have a little bit of an increase in power. We go to retimed, it really gets significant into the 18 watts for a by 16 PCIe interface. So the standard for external PCIe connectivity is the CDFP connector, which is standardized by the SFF TA1032. CDFP has been around for quite a long time. It actually was developed over 10 years ago for Ethernet connectivity, and then improved gradually to meet up to the speeds we have today. When it was originally developed or designed into the CopperLink spec, it was really thought of as a passive-only type solution. We TE and some others worked to add power to it in order to enable it to be a truly fully active solution as well. Now, the passive cables can support approximately about 2 meters of length in passing all of the PCIe specifications. In practice, you can actually get much further. Last year, right here at the OCP Summit, TE demonstrated a 4-meter cable. Now, this was a Gen 5 cable with Gen 5 connectors, and we were actually running Gen 6 traffic over that 4-meter cable with an acceptable bit error rate. So we know that different system architectures can definitely support more than even what the standard would otherwise allow. And then when we add silicon to that, now we can get to even greater lengths. Now this is an overlay of performance of the cable that we presented last year, I think of the 4-meter passive, and you can see as compared to the Gen 5 limit line, it's below it. Now again, this cable was actually functional in a PCIe channel. Now when we look at our active CDFP cable, now this is actually a 4.5 meter, so it's a little longer, and its loss characteristics are actually well above the line out past Nyquist. And so we know that as we add the active silicon to it, we're getting a great performance increase. Now the TE product that we've built, we have a picture of that in the upper right, is actually, it's a half redriven cable, standardized with, compliant to Gen 5, and it's a by 16 interface. Now that can easily be scalable down to a by 8 and even a by 4. And it's fully compliant to the PCIe specification, the TA1032, so it's interchangeable, and that's I think a big deal, where you can then use, if you have a redriven, you need long links where you use longer cables, and you can use for shorter links you can use the passive cable, so you can mix and match, so it's the same form factor. And so we're integrating in this particular cable 2 by 8 linear redrivers. And the one thing I want to emphasize the most is its low power. We've heard that again and again. In Andy's talk yesterday, talked about the huge amount of power increase. And so on all these links where we have to get to these further distances, we want to minimize that. So this is about 220 milliwatt per PCIe channel. If you compare that to a retimer, that's about a little over a watt per channel. So it's a great savings. If you don't need that extended reach that maybe a retimer will get you, redrivers can really do the job. So our initial products that we're releasing is really a by 16 to by 16. Again, as I said, we can scale that to by 8 and by 4, and we can also do breakout cables if you're going from a by 8 to, a by 16 to maybe 2 by 8s. Our current target is a 4 meter, but again, we know we can get longer reach, and it's really if you have a purpose-built channel, they can support longer lengths, even though it might not be totally PCIe compliant. It can still work for you. And then right now we're working on the Gen 6. We're working with our silicon partners for a Gen 6 designs right now. So I encourage you to come to our booth and you can learn more about it, and I can show you an actual cable. Thank you.
Okay.
Eric?
Here is Arthur from Molex. So thanks for Brian and Ashika as introduced. So from Brian's slide, you can see we already have see the challenge from the external cables, and now for the internal cables, we seem to facing slight different challenges. Unlike the external cable, we are looking for much longer cable lengths. For internal cable, when we from the Gen 5 to Gen 6, of course, some customers we would like to looking for seeker cable, so we can still go with a passive solution. However, due to the seeker cable, that's also more stiff and not easy to bending. So some of customers start to looking for a tiny, small cable, not from 30 to 29, 28. Instead of that, they will go looking for 32 or 34 wire gauge. So the thinner cable that will provide a much easier cable routing, more flexibility for this kind of orientation. So currently, we also looking for to use the redriver on the internal high-speed cable. The reason, as Brian just mentioned, because the retimer, the power consumption is too high, and also for the internal cable, typically we don't need to increase such high insertion loss budget. We only need very limited numbers. So here we can see that's some of the benefits. From the redriver that already provide enough insertion loss budgets, and from some test result, we can see the ICR can still keep in larger than 30 dB, but the loss we can increase quite a lot. And we now can use 32 or even 34 gauge to the very small cable with a redriver to support PCIe Gen 5, Gen 6, and we are also looking for the Gen 7 application. From the thermal, since in the picture, you can see there's IR pictures. Even without the airflow, the temperature rise is still very limited. It will not impact all the thermal inside the chassis. And also, very good things is we already see some new form factor, for example, the TA1035, the pin count is something like the 74 plus 6 pins. So the 74 pins is still keep exact same the pin count we typically use, but the extra 6 pins are already good enough for the power, ground, and I2C for the EQ adjustment. Again, that's similar as what Brian say. You can easy to choose to use active or passive cable in different scenario. Yeah, so just depends on those 6 pins is a connection or no connection. Okay. Then I will pass to my colleague Erica to describe more the season test things.
So we build a sample with the 1035, the 80-pin connector with a 32 gauge cable, and the cable length is 1 meter long. I believe 1 meter long is surely the pretty covered 95 usage for the internal cables. Okay, so we built the redriver IC at one side of the cable and two double side on the pedal cars. Okay, So this is a simulation and the test data. Look at the center, there's the test data. So we can see the redriver IC actually working well. And it proved our theory to have the ICR larger than 30 dB. So that kind of good result for this cable. And also we do the system test. So we input the 32G bird, and we can see the result here. So you can see also the very good eye diagram here. And this is Gen 5 IC. But toward the Gen 6 and Gen 7, we also do the Gen 7 pump for the signal simulation. So you can see the left side, the Gen 6 system insertion loss level is 32 dB. The standard signal, you can see the very good eye diagram. But if your system, unfortunately, if your system have 42 dB, we input that, you can see if the signal was not good, if the eye not opening, you can see the middle side, the photo here. And with the redriver IC, we can get the good result at the right side. All right. That's all our testing. So this presentation mostly covered the Ashika's Gen 7 design and the external the redriver IC and also the external the redriver IC cables. So hope it's a contribution to the development of the PCIe Gen 6 and Gen 7. Thank you.
I have one question for redriven cable. Normally, the driver doesn't have any adaptive equalizer feature, but cable doesn't know root complex to connector loss. So how to optimize the driver equalizer for various case of root complex to connector?
I would have to get back on that. I don't have that information right now.
Okay. Right.
Hey, Brian. Hope you're doing well. The plot you showed for the active cable,
Yeah.
was that mated to a Gen 5 connector as well?
That was also made into a Gen 5.
Okay, so there should be an improvement with the Gen 6 connector that comes out whenever.
With the Gen 6 connectors, they would perform much better, and
Okay.
There would be an improvement there. The other thing I kind of forgot to mention was this is all based on a 30-gauge cable.
Okay.
So with a larger diameter, if we went to, let's say, a 28-gauge, we would get an improvement as well.
Gotcha. Thank you.
So, one question. So your redriver is also PCI Gen 5 redriver, right? It's not Gen 6 redriver.
It's a Gen 5 redriver, yes.
So if it's Gen 6, it should be better.
Yeah, yeah. We're working with silicon partners now to look at drivers.
And we have active system demo in our booth. So if you like, you can drop by to see the active cable connect the system. Live demo there in Molex booth. Thank you.
So I have a question on the new connector proposal. We're looking at the same thing in Ethernet, but PCIe is extremely cost sensitive. How do you see the feasibility of that if you go to a two-piece connector? Maybe that doubles the cost. Is that even feasible for PCIe to do that despite the performance benefits?
You're talking about the internal cable, the new connector, the new form factor?
She's talking about the Gen 7 connector.
Yeah, I'm sorry, I forgot the name. I apologize.
That's okay. Yeah, we think we can make it because it's on a schedule for sample in January. So it's based on stamped and formed, so it makes it affordable, yep.
Thank you.
Thank you.
That's it. We're done. Thank you.
Thank you.